So all of you, please turn on your camera, students.
Good evening, Usha ma'am.
Ma'am, எப்படி இருக்கீங்க ma'am?
Fine ma'am, fine ma'am.
Thank you ma'am for joining, for sharing your knowledge with our students.
Oh, it's a pleasure ma'am that you always remember us.
Yes ma'am.
Thank you so much ma'am.
Thank you ma'am.
Yes, ma'am. Shilpa ma'am, we will start the session, ma'am.
Yes, sure, sir.
Yes, ma'am. Durga ma'am.
Yes, sir.
Yes, ma'am. Yeah, you can start the session.
Good evening, all. So I invite our faculty members and students and our chief guest, Dr.V.Jean Shilpa, Assistant Professor, ECE Department, B.S. Abdur on Crescent Engineering, Crescent Institute of Science and Technology. He has 14 years of teaching experience and he did a BE in Golden Valley Institute of Technology on 2006 and he completed M.Tech in VLSI design at Vellore Institute of Technology and she did a PhD in hybrid CPU FPGA design for high performance computing. She received she organized more than 20 workshops and she has undergone 5 days industrial internship at QMax Testing Solutions and organized a 5 days industrial training program on Internet of Things and cloud interface. She has published more than 30 papers in reputed journals and 30 papers in national and international conference. And she has published 2 patents and she delivered various guest lectures with hands-on training in Tanner Tool, LabVIEW, Xilinx Vivado, Cadence Tool, etc. And she received Best Paper Award in the second National Conference on Current Academic Research in Communication and Networking. She received a LabVIEW Associate Developer Certification by NI on 12th June 2017. Once again, I invite our chief guest for the work for the hands-on training on Xilinx Vivado. Now I hand over the session to Dr.V.Jean Shilpa. Welcome, ma'am.
Thank you so much, ma'am, for the brief introduction. I am always indebted that we have a strong bondage between both the institutions. Whatever we conduct, faculties and students participate from your institute, and always they keep us in good books so that knowledge sharing will be for the betterment of both students and faculties. So thank you so much, sir and ma'am, for this opportunity. Hope I will be able to deliver the insights of Xilinx via Vivado to the students that they may take up projects in VLSI and bring many more laurel to the institution. Thank you so much, ma'am. Now I'll start my presentation.
Yes, ma'am.
Yes, ma'am. Thank you, ma'am. So others, now you can turn off your cameras. As students, so you can utilize this session. So ma'am is expertised in EDA tools. Okay, so whatever doubt you have, so please raise and utilize this session. Thank you, students.
Sir, am I audible now, sir?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Is my screen visible, sir?
Yes, ma'am. Yeah.
Okay, sir.
Ma'am, sorry for the interrupt. If possible, so please make it in slideshow mode.
Yeah, it is loading, sir.
Yes.
Sir, is it full screen for you now, sir?
Yes, ma'am. Yes, ma'am.
Yes.
You can.
Okay.
Yeah.
Thank you, sir.
Yes.
So, students, so we will be handling a session today on Xilinx Vivado. So before going into this tool, I'll give you a brief introduction about why we have shifted from Xilinx ISE, which we have been using for so many years, and why the platform is shifted to Xilinx Vivado. Now, previously when we were using FPGA boards, I'm sure that all of you will be aware of what is FPGA. Can anyone tell me what is the full form of FPGA? What FPGA stands for? Okay, let me go ahead. FPGA stands for Field Programmable Gate Arrays. So as the name itself tells, field programmable gate array in the sense, we have a board which is having a sea of gates. Gates, all of us are aware that it is purely logic gates. Now, when a complete board is made up of full of logic gates, and I'm able to program that gate, I call that as field programmable gate array. Okay, it's not only gates. Using many gates, we try to form smaller components like LUT slices, which are there inside an FPGA. So that's a big topic of how the architecture of FPGA is made. Now, when the FPGAs were introduced and when they came into market, FPGA consisted of only these array of logic gates. But when there was a shift to the higher families, we call them as families of FPGA. When we started to shift from, say, Spartan family or Vertex family or Kintex family, we were almost using this Xilinx ISC. When there was a shift from this uh, families which we were being using traditionally, we started the company started to bring boards which had processors incorporated in them. See, the beauty of VLSI is why we are able to sustain in the market, wherein there are so many embedded boards coming inside the market day to day. You can see that very low cost embedded boards will be there in the market hitting every day. But, but still, we have a separate place for VLSI boards. So what makes a complete difference between this embedded system boards and VLSI or FPGA boards is that these FPGA boards can what to say, can be a platform for experimenting experiments. That will be the first application of an FPGA. You can experiment FPGAs, test it, so that whenever you want to make a big design which goes into a multi-core processor or a what supercomputer or something, you initially have to test the design. So that design has to sit in a particular platform, so that it if I say the design is tested in FPGA, I'm authenticating that the design can work anywhere in any platform. So mainly FPGAs were introduced for testing purpose, wherein before putting the hardware or digital design into a processor kind of platform, they used to first test it. So initially it was used for testing. Later on, seeing the advantages and applications that are being developed in FPGA, the company started coming with adding processors inside FPGA too. Like ARM processors were incorporated inside FPGA. Now Intel is also working with processors having FPGA inside it. Now, why is such a big company Intel, which has so many high performing processors, still wanting FPGA inside that Intel processor? They wanted because one big what to say wonder of FPGA is it is reconfigurable. What is the meaning of reconfigurable is you put a design, you make it work. Okay, now I want to make some modifications in the design. But if I buy a mobile, I'm okay with all the features. Say after 2 or 3 years, another brand of mobile is hitting the market, or another version of the mobile is hitting the market. They may have special features incorporated in it. Now, if I have an FPGA inside my mobile, I will have the option of upgrading my hardware also. like how you upgrade. See, say for example, your WhatsApp is outdated. So you may get a message that you need to upgrade the version of the WhatsApp. You will not buy a new mobile. You will run it in the same mobile, only your software will get upgraded to the next version. Similarly, the world is going towards developing hardwares where it has to automatically update without the help of a designer. That's why the raise is so much for FPGA. It is the best platform for reconfiguration wherein you can upgrade your hardware also. So this Xilinx Vivado is the next version of Xilinx ISE, which we are all been using in the lab. One beauty about this field of VLSI is that the main languages which we need to know as a programmer, if you are a hardware designer and a hardware programmer, it is enough that if you know Verilog and VHDL to the maximum extent of what to say, if you are very well with the programming concepts of Verilog and VHDL, you can get into any of the core companies that are working in VLSI. So it's not like the software people wherein every day they get a language released in the market. You have to, what to say, pay for it, train on it, you start working, and after 3 or 4 years, it is getting outdated and you have to go to a new platform. For us, it's not like that. As VLSI design engineers or electronics engineers, it is enough that if we are either good at Verilog or VHDL. It is made so simple. Okay, people start realizing this very late. And so when these processors came into the FPGA board, it was difficult to continue with the ISE tool because they were helping us only in making small logic circuits, and they were not able to build processors that are there inside an FPGA board. So this Xilinx Vivado is a higher version. So we will see through the slides what are the different features added with this Vivado, so that how it is different from ISE. So the agenda of this workshop will be, I'll be introducing you all how to work with the Xilinx Vivado and give a small hands-on training on Xilinx Vivado. So basically it is a IDE tool. Okay, what is that IDE tool? It is an integrated development environment tool. We call it as integrated development environment tool. Whereas if you take Xilinx ISE, ISE is integrated synthesis environment. Okay, synthesis in the sense it is one step lower than the development. So now the name itself is changed as integrated development environment, or IDE for Verilog. Okay, so we are going to program this IDE tool using Verilog and download the compiled code to the FPGA board. Now this we call it as Vivado Design Suite. Okay, because it is a tool which is not only going to help you compile your Verilog code, there are so many things that you can do with this Vivado. That's why it is called as Vivado Design Suite. So it supports FPGA series which are greater than 7 series. Okay, we have 6 series of FPGA, 5 series of FPGA, and 4 series of FPGA. This FPGA supports series greater from 7 and greater than that, ultra scale, and all the recent families which are coming to the market like the Kintex, Artex board, Pink board, etc. So the main important feature that is well designed in this Vivado design suite is it has an excellent placement and routing algorithm. I'm sure that if you know the flow diagram of VLSI, we know that where this place and route will actually fit in the entire VLSI design flow. So this place and route will be in the backend flow, wherein how well you place your cells and how the wiring is made or routing is made between the cells makes your device very efficient. Okay, so that is very well planned in your Vivado design suite tool. And also one more special feature that is included in this Vivado is Vivado has a package called as high level synthesis tool. Now we don't expect that only hardware engineers who know Verilog can work with this Vivado. We also there is also an option for people who can write C programs using C or C++ kind of syntax. in Verilog itself and develop their code, and that can be gone for optimization. So that can be done in this high level synthesis tool. And one more special feature of this high level synthesis tool is, we all know that if you take up a processor, the main architecture which will be there inside a multi-core processor is parallelism or pipelining. So that parallelism and pipelining can be easily done in high level synthesis tool without putting the designer's effort. I need not program, okay, I need not change the architecture. I just give my design and ask the tool that increase the level of pipelining. The tool will be able to increase the level of pipelining for me and do the required analysis. So that is one special feature added in this Vivado design suite tool. Now this slide shows you a clear picture of how many different tools we used in Xilinx ISE to generate the synthesis of the file, whereas this Vivado has a small one design suite in a package. So initially we used to open a project window, we used to compile our codes, then we used to use Xilinx plan ahead tool to put the pin assignment when we are going to dump it in the kit. Then we are going to synthesize it. Then we are going to use, we were using Xilinx impact tool to download in the FPGA, and all this only made up this Xilinx ISE environment. Whereas when you come to Vivado, it is just one window and all these features are incorporated in this one window. That is a speciality of Xilinx Vivado. So it is a new integrated graphical user interface. Okay, that is one advantage. You need not open, if you work with Xilinx ISE, your user constraint file, okay, UCF. This file, you will put all the pin configuration required for the board. So I need not open the Xilinx plan ahead separately to give the pin assignment. Everything is incorporated inside this Vivado itself. And also I had a separate downloader called Xilinx Impact to download my code in the bit form into the FPGA. Now that is also not required because I have a direct option for me to generate my bit files in Vivado. Okay. Any doubts so far? Able to follow?
Yes, ma'am.
Yes, ma'am.
Okay. One second, my slide is not moving. Just give me a minute. Now, can I know that how many teams here are working with FPGA? Any final year students? No? Okay. Okay, what do you actually do in the lab, VLSI lab? So all of you are in holiday mode, so no one wants to talk. Okay, let me continue. Vivado GUI. Okay, this is the screen of how your Vivado GUI looks. So I'll tell you what are all these blocks. We have so far seen only Verilog programming in Xilinx ISE, but here you can see a few blocks which are all interconnected using so many wires. So I'll tell you what is that later on. And we have one more special feature in Xilinx Vivado. Sorry. Able to see my screen? Can someone acknowledge?
Yes, ma'am.
Okay. Yeah. One more special feature which is added in this Xilinx Vivado is the IP integrator. All of us know that when you are working with bigger designs, say like you have a processor which is an ARM processor, you want to connect that ARM processor to a memory unit. So when you work with Xilinx ISE, all you know that is you have to write a simple code in Verilog to design a memory, and interconnect that memory with the main program by what to say structural mode of modeling. But that is not required here. So you have something called as IP integrator. What does this IP do actually is already we have the blocks which are designed by Xilinx people for us. Like they have designed so many what to say converters you have many decoders, encoders, you have an protocol which can support Ethernet, and you have many bus interfaces like AXI. So you need not waste time programming on all these basic stuffs. All of this can be dragged as an IP, just as a IP, and connect to your design. So what happens is actually when you're working on bigger designs or complicated designs, you need not spend time on the blocks which are already designed by a third party. So they will be able to give you all these blocks in your design so that you can spend your most of your time developing your own module than the peripherals which can be connected to it. Now, say for example, you make a unique design and that design you want to protect it and you want to make it as an IP. So here you can build your own IP and you can sell it actually to a third party person who wants to access that IP. Say you have designed an audio controller, you can have that audio controller as an IP, and if a third party wants to use that audio controller for his design, he has to ask you the license, for which in turn you will be paid, and all that can be done in a IP integrator. One more special feature of this IP integrator is if you have a MATLAB code, that MATLAB code can be converted to an HDL code using HDL coder, which is there already in Xilinx Vivado, and directly you can take that MATLAB code into a HDL code and wrap it up into an IP and bring it into the Xilinx Vivado environment. So this is one very good feature of Xilinx IP integrator, wherein people try to find new things and try to help the other community people who are in VLSI and want to work on it. Okay. So now let us go to our small part of working on the tool. So before working on the tool, we should know the definitions of these three terms: simulation, synthesis, and implementation. Now we were stopping in Xilinx ISE with these first two terms, simulation and synthesis. Now we are going for simulation, synthesis, and implementation also. So we will try to know the definitions of all these three terms. Simulation is nothing but you will take your design, apply some inputs, and see what output signals you get along with the delays. So you'll get a waveform, you check whether you're getting the correct waveform. Synthesis is a process of, see, before putting your design on the board, you want to check it virtually in the tool. So the tool will give you an abstract result of how much power, timing, area is taken for your design. So that is synthesis part. Implementation part is actually when the design sits on the hardware. After the placement and routing takes place, what exactly is the power calculated? That will be done in the implementation process. So all this is possible using Xilinx Vivado. So can you have Xilinx Vivado on your laptops? Yes. So what Xilinx has done is, for the people who are very much interested to work in Xilinx, you can go to the Xilinx website. You can create a login using a Gmail ID. Basically, go inside to the downloads and check for the web edition of Xilinx Vivado. So in the web edition, it is free. They won't ask you any license. You can just install and use it for a period of 1 month's time. I don't know whether it is extended now. So you can use it, take your results, and you can publish them also. So when you go for, so let me come to this project summary later before telling about what is there inside the tool. So all of you know that this circuit is a small half adder. So half adder is one which is going to add 2 bits, give a sum and a carry for me. So I have put this half adder in the data flow modeling. So as we all are aware that in Verilog, we have actually 3 different levels of modeling: data flow, structural, and behavioral. We should know exactly when to use data flow, when to use structural, and when to use behavioral modeling. So if you see in this particular slide, this is the small program written for a half adder. So module half adder, I have declared the inputs as A and B and declared the outputs as sum and carry. Now, assign in the sense it is a keyword which is used for data flow modeling. Assign sum is equal to A and B, carry is equal to A or B. This is the simple program written in data flow modeling. For the same program, I have written again a simple test bench wherein I'm giving all the possible inputs A0, B0, A0, B1, A1, B0, A1, B1, and I'm finishing the program. So this part of the program will tell me how to give the inputs required for that particular design. So let me go to the tool. Yeah, basically when you install the tool in your system, you have to go to Start, All Programs, then come to Xilinx, Design Tools. Yeah, there Vivado, and click on Xilinx. I've installed a very old version, that is 2014.4, but that is enough to work with the basic designs. So if you have a processor which is i7 and if you have Windows 10 running on it, you can go for higher versions of Vivado. So just click on this, you will get this window. Okay, so this is the Vivado window. So I have this options here. Let us know what are all these options. This is an option to create the new project. Already, if a project you have done, you can go and open those projects here. There are some example projects you can work on it also. So let us go and start a new project. Okay. So this screen will open for you. Okay, this is a new project. So what I've done is it will take time for us to type all the programs. So already I have typed those programs and kept for you. Let me open those and show. But I'll tell you basically how to start up a project. Okay. So here you go. Create a new Vivado project. Click on next. You have to give a new project name. So by default, it will start giving the project name as 1, 2, 3, 4 like that. So this is the default name given. So I like to maintain the same default name. This is the name of my project. And here there are different types of projects that we can create. One is RTL project. This is post synthesis project, IO planning project, imported project, and configure an example embedded evaluation board design. Now, since we are going to do with a small Verilog code, it is enough that we click on RTL project. Already, if you have a project which is synthesized, then you can go for this option. If you want only for IO planning, that is how your design can be configured with the other IO devices, then you can go for IO planning. Similarly, the other options. So for now, let us go to the first option, RTL project. Now here it will ask you whether you want to add sources. Already, if you have a Verilog file typed and kept in your system ready, you can go for this option, add files, add HDL and netlist file. If not, go for this option, create new file. So it will ask for you to create a new file. So I'll give the file name as half adder or something like that. Then give OK. So here it will tell you it has created a new file, half adder. You should make sure that it is .v. .v in the sense it is Verilog. Select your target language as Verilog. So here you have an option to change from Verilog to VHDL. Now currently we are going to work on Verilog. So we are going to select Verilog. The language, simulator language can be mixed by default. So you just leave it like that as mixed. Click next. Here. Now I told you there is an option for adding IP. Now say for example you have written a big code and you want to add the third party code into yours or a DSP component into this or an embedded system sub design file into this. You can just go and add these files if you have it for your project. Now we do not have something like that. Then if you have any constraints like timing constraint, if you have or power constraints you have, you can click here and give a constraint file. So all these features will not be there in Xilinx ISE. Then next you will go for selecting the board. So here you have to be very careful. Whichever board is there in your university, you can select that particular board. For now, I go for the very basic board, which is taken in by Vivado. So I go to general purpose, then I go to Zinc 7000, then I go for Zinc 7000 subfamilies. In the package, I will select the lowest package, CLG 225. Then see how I do all this is you will have an FPGA with you. On the FPGA, all the specifications will be written. You just have to see that particular IC chip and you have to update all this. Okay. So this is the board. Yeah. Click next. So what all you have done for your project will be given as a summary here and click finish. So it will take time for you to create a project. So it is loading. For what all specifications you have given, it is loading. So here it is asking what are all the inputs. See, Xilinx is a very nice tool. It will do half of your task of assigning inputs and outputs and all. So this half adder has two inputs. So let me assign A, B, sum, carry. Now this sum is output, carry is output. Okay, so I'm fixing all this and giving next. So what is happening? You can see the small window. The small window will tell me design sources are half adder.v. Just double click on it. You will get what you have done. So module half adder, input is A, input is B, sum is output and carry is output. So what to say, a framework of your code is already written by the tool. Okay, so already I have done it for you. I've written the code. I'll just show you. Yeah, this is the code. Assign sum is equal to A and B. C out is equal to A or B. Okay, so this is the code. Now when I want to test my code, what happens? The next thing what I have to do is just right click on this half adder.v. Always when you are programming with Verilog, you have to write the test bench. Okay, so what you will do here is right click on it and go to the last option, add sources. In this add sources, there is an option for you, add or create design sources or add or create simulation sources. Now I'm going for simulation. So click on this, add or create simulation sources. So here it will ask me, do you want to create a separate code for testing your program? Yes, give yes, create file and give the name of that file as test underscore half adder. Give OK and finish. So it will create a test bench for you. Test bench will not have any inputs. So you just give OK. So a test bench is created for you. So where will the test bench sit? This is your design source. Go to the simulation sources and check your test bench will be sitting here. But one feature of test bench is that when you write a test bench, this program should go inside test bench. So what will make that happen is, let me open the test bench. So this is the test bench. So test half adder, register AB. See, you have to declare the inputs as register and outputs as wire. So inputs are declared as register AB, wire is declared as sum and cout. You're calling the half adder, initial, begin, you're giving all the four options which you are going to test it. Already I showed you, and give this last command $finish. $finish means your simulation will end with that. If not, it will keep on running. So give end and end module. Now I have finished my design. Now if you see there is a plus sign added to this half adder, click on this plus sign. You can see inside this half adder there is a, inside this test half adder there is a half adder program. Okay, so whenever you call this half adder in your test bench, like this half adder space H is called as UUT, unit under test. When you call it, automatically the program will go inside the test bench. What is the meaning? I have written a program to test my design. That is called as the test bench. So it is gone inside. If there is any error, you will not get that branching. Okay, the half adder will stay out. So if you have written correctly, that branch will go inside. So click on this test half adder. Okay, then the first step what you will do to exactly test your design is run simulation, run behavioral simulation. Click on it. So it is taking time to run. Compile your code. So sometimes this tool gives you some messages like this. 1 second. Once again, there is some problem in the tool. So if there is improper shutdown, sometimes we get this error. I'll do one thing. I'll just go to this window, copy the same program here. Okay. Open this test bench. Copy the same program. Save all. So you go to file and give save all files. Yes. Now you can see this test adder has taken inside this half adder. Click on this and run your simulation. If you have a very good high-end processor, this process will run very soon. As always, when you're installing Xilinx, you should make sure that for running this Xilinx efficiently on a hardware, what type of processor will support it. If you install in that kind of machine, it will be better for you to get results quicker. So I'll just show the waveform which it has generated already. I've put it in my PPT. So this is the waveform. It will be good that, yeah, it has come. Yeah. So 0, 0, A is 0, 0. Then again 0, 1, 1, 0, and 1, 1. Okay. 1, 1. I'm not able to get here 1. Yeah, 1, 1 is the last condition. Since I've given this finish here, it is finishing off with the last command. Okay. So this is the basic half adder which you will do. Now after this simulation, we'll go for something called as open elaborated design. Okay. Click on it. what exactly happens in this elaborated design is, see, as a programmer, we will start writing the code. We will get the output waveform. We know what is the structure of this half adder. So yeah, I've put the structure of this half adder. So this half adder is having one XOR gate and one AND gate. So practically, I should see that in the tool that my tool is able to generate this particular hardware. So I have to confirm it. So I go for the process of elaborating my design. So let's see what's happening in elaboration. So it's 50% completed. Let me check if I can do it here. Yeah. So you can see how the tool generates. It's using one XOR gate, okay, and one AND gate. Okay, fine. So this is a simple RTL schematic of how the tool generates this particular what to say code into a circuit. Now the next process will be synthesis. Synthesis, what exactly it does is, I've given what will be the target board. Target board is zinc. So for the target board, I'm running my synthesis. So synthesis will start running and calculate how much exactly it is going to occupy the what to say space in the board. So it will calculate the space for me. It will calculate what is the timing for me. It will calculate what is the power report for me, so that I'll be able to see before the program is sitting on the board. I'll be able to calculate what is the power, timing, number of gates used and area used. So all that I will be able to calculate. Okay. So it is still running. It takes some time. So meanwhile, before it finishes the, what to say, synthesis, because it will take some time, I will show you the remaining designs which I have already synthesized in Xilinx. Yeah. Okay. So this is a full adder. Full adder, I've written it in data flow modeling. Okay. So data flow modeling, in the sense, I'm using assign statements to get my sum and carry. Then I've written a test bench to generate the waveform from Vivado. Now when I elaborate my design, this is the circuit generated for the full adder. Okay, let it still loading. Yeah, this is the RTL circuit generated for my full adder by the tool. The same code, when I write it in behavioral modeling, I'll show the code inside. It's very what to say. Let me try to zoom it. Yeah, it goes beyond the page. So I will try to zoom it. You will use a case statement or a if statement to write this particular code. So when you're using such kind of statements to write this code, as a designer, it will be very easy for us to write a code without knowing any logic, only using behavioral modeling. But when you see that for the same full adder, the RTL diagram or the RTL circuit which is generated for me is utilizing so many multiplexers from the library. Whereas the RTL code which I have written using data flow modeling is using only few gates. The same full adder, when I write in behavioral modeling, you can see the number of wires, number of gates it is taking, and it is just a waste of energy when it is going to sit on a board. So as a designer, you have to be, that is why we always have a distinction between a software engineer and a, what to say, an expert who can do good coding in Verilog. Okay. So this synthesis is over for me. Yeah. So I told you here, See, the same full ladder is you using more than 10 to 20 multiplexers, and it is using some gates, whereas I'm able to complete the same full ladder using a maximum of 7 gates. So if a designer who doesn't have knowledge in Verilog or doesn't have knowledge in digital design, or he doesn't know the equations which actually generate circuits, he will start programming using behavioral modeling. When they do the programming and behavioral modeling, ultimately the circuits which consume more power will sit on the FPGA rather than the circuits which are really optimized. The same full ladder I'm able to do using the data flow modeling. Whereas when I go for behavioral modeling, this is the big circuit generated. Similarly, when I go for the structural modeling, the circuit which is generated is this. Okay, this also I can comparatively say that it is not as big as the circuit which is generated for a full ladder, but you can see only few blocks are there. See, I just click on this block. Inside this block there is a XOR gate and a AND gate. So like that, structural modeling is a modeling where it will have small blocks inside them to carry out the operation. So let's go back to the tool. Now you can see here, just expand and see, zoom and see. This much amount of space is taken inside your FPGA to make your adder design and sit. Okay, your entire board is empty. Your FPGA is occupying only this, your half adder is occupying only this much space. So let me check here the project summary. Project summary is one in which it will give you all the necessary information that you want with respect to this particular code. Out of 100% of this availability of components in this board, my design is using 7% of input output pins and 1% of LUT. LUT is lookup tables, which is there inside the board. So this will give you the utilization summary of what exactly is the hardware used inside your board. Next, we will go to report power. When you go to report power, there are some conditions given for you. I just give. So what are the conditions given in this report power screen is, it will tell you what should be it. You have an option to set at what particular temperature this design is going to work. So I have the option of changing the temperature here. Now I have given a default value of 25 degrees Celsius. Like that, I can set up the environment surrounding me, what all different supply voltages will be given inside an FPGA, then just give OK. So if you give OK, if you give OK, it will start generating what is the power. It is telling you that you're not using any clocks inside. Okay, you're not using any clocks inside. So this is your power report. Yeah, this small graph will tell you total of 0.510 watt of power is used inside your chip, out of which 17% is static power, 83% is dynamic power. Okay, out of this 83% of dynamic power, 9% goes to the signals, 90% goes to the IO pins, and this green is a very small amount, 1% for the logic which you have actually implemented. So the percentage of how much power is used for all this will be given. Here the operating conditions of the chip is given. Okay, so you can check this particular power, how much your design is actually utilizing, and you can decide on whether you want to go for low power applications, or if you want to less the number of transistors or the components used in your device in order to bring out an efficient design in VLSI. So go for report utilization. Okay, so this you will minimize. Yeah. So this report, we'll go for the summary here. So in this summary, you can see, yeah, 1 minute. We need to run this implementation. Okay, go for running implementation, so that actually when this product, when this code which you have designed sits on the board, what exactly it is going to consume in the board, you will get a very brief view of the summary. So it is still running. This status tells you that the implementation is still running. Process is still going on. So once this implementation is complete, you have an option to open your implemented design. When you have an option of open the implemented design, you can see all these reports. Timing report, clock networks. When you go for sequential networks, you can go for clocking networks. You can check for errors, you can check for noise, then you can check how much percentage of your hardware is used. Then you can see what is the power, overall schematic you can view. So all these options are given to you in order to analyze your circuit. Okay, analyze what exactly you're doing in the circuit and try to optimize. So it's a very nice tool wherein you need not only program, but the way you program will be projected in the reports that are generated. So as a design engineer, I can give hardware design of full adder to anyone. But if I see here, this is also a full adder for me. This is also a full adder for me. But when will a customer be happy? He will be happy when you're utilizing very less number of components in order to design your circuit. So here it is a pool. I am not happy with this pool to design a small full adder. So what I do is I will try to minimize. I will try to minimize by bringing in experts who can work in Verilog. So the world is in need of people who can work efficiently with Verilog and VHDL. The next level is system Verilog and system C. Only when you are efficient with Verilog, you will be able to explore what is there in system Verilog and system C. So have a good programming habit of always keeping in touch with Verilog, so that, see, very few languages of you people have an option as hardware design engineers to learn. So it's actually a boon for you, so that you can become master of these languages. So try to use this Verilog very commonly in your day-to-day lab sessions, so that when you become familiar with Verilog, you will be able to read all these reports. Okay, we have to be very, very patient to analyze each and every report and decide that which circuit exactly I can use for my application. Okay, so still the what is the implementation process is running. So only when it is completed, I will be able to show you how much exactly is the total power consumed when you are making the design sit on your hardware. So that will take some time. All placement and routing, everything will be running, right? So it takes a lot of time in the background to pull these cells, select the board which you have taken, place these boards, place these cells on the board which you have developed, and do the placement and routing, and actually calculate how much time it has taken. So let's wait for a few minutes for this implementation to complete. It will give you a best result. I'll see that if I have some reports I can share with you. Open implemented design. Yeah, it's done. Now we will go to open implemented design. Now once this open implemented design is running, you can go again to this project summary and check that you will get the actual power reported when this particular design is going to sit on my FPGA. Okay. See, because it has to generate all these reports again and tell you how much exactly it is going to take. Okay, when it is actually, I'll just show you this last report. Now, this report will tell you total on-chip power when your design sits on that particular board operating at 31.6 degrees Celsius. What is going to, this is going to be the total power and this is going to be the total area consumed. This is enough for us to know now. Later on, when you have time, you individually take time to read all these reports and try to understand how better your design is. Okay, so for today we have taken a simple half adder. We have seen how to do synthesis, simulation and implement your design, and we have seen how to study the power and the utilization summary of our design. So the same thing I had done for a full adder also. I thought I can do it for a full adder also, but it takes a lot of time because the tool takes a lot of time to run. So what I insist you all is download the web version of this Xilinx in your laptops. Develop small design. You don't need any licensing. You develop small designs and check, make a power comparison and start publishing results. Okay. So I'm done, sir. If people have any questions, they can raise.
Yes, ma'am. Thank you, ma'am. Students, if you have any queries, you just ask, ma'am. Third year students and the students are doing project on VLSI platform. You just get the clarity from ma'am.
You can also contact me later. Yes, ma'am.
Good evening, ma'am. I'm Lakshmi, ma'am.
Good
From
evening, ma'am.
ECE. Ma'am, does Vivado supports VHDL variables, ma'am?
Yes.
That
It supports. You can program both in Verilog and VHDL.
Okay, ma'am. Okay, ma'am.
That is not a problem.
Yes. Yeah, one more thing, ma'am. In this coding, we have used end and end module in the end part, right, ma'am?
Yes.
So whether it's necessary of giving this conditions, we have to use end or it's enough using end module, ma'am?
Actually,
if you are
when you take up this test bench, I'm beginning a loop here using a begin. Okay, whenever I put the statement begin here, always I should end. Also in behavioral modeling, let me show you this. In behavioral modeling, I'm using an if loop. Okay, if loop. So wherever I'm using this begin, I have to end.
Okay.
When you will be using begin and end is when you have more than two statements or three statements, that is more than one statement, you should always put them inside this begin and end. So that tool knows that they belong to one category. So one begin I have here, that overall begin will end at the final stage.
Yes, ma'am. Thank you, ma'am. Thank you so much.
It's okay, ma'am. My pleasure.
Students, any other queries from third years and second years?
Ma'am?
Yes.
Ma'am, can you tell me what are the requirements to enter into the VLSI industry, ma'am?
Basic requirement you have to be very good in any one of the programming language, either Verilog and VHDL, and you have to be very good in understanding the subject VLSI design. That is enough for you to enter into the VLSI industry as a fresher. Okay. So there are many.
Either we want to complete a MTech or we doing a course in a
See,
house.
MTech, if you are completing, you will be, it is easy for you to enter into VLSI. That is what to say, dream companies which are there in VLSI. Say the companies which work on processors, they will directly take you because they know you. Years you have spent working and learning with VLSI tools and VLSI subjects. So they will all expect that you have to be very good in cadence as well as Xilinx. So it is enough that you are master of these two tools and you know how to program, and also you know, and you should be good in analyzing the CMOS circuits.
Okay, ma'am. Thank you, ma'am.
It is what to say, good that you practice your coding as well as your circuit designs in cadence or spice tools is also enough. So here I would like to bring to your kind notice that we are organizing a workshop for people who are aspiring to either take up a MTech degree in VLSI or go into VLSI companies, wherein the communication protocols which they are using with FPGA boards. So we are getting an expert from a VLSI company called as Smart SOC. So he'll be training you all on how to design protocols to connect peripherals to FPGA board. So we were that's a very happening field in VLSI industry. So anyone interested, you can contact me later. Yes, any more queries?
Students, is there any queries?
No, sir.
Okay.
Ma'am, hello.
Yes, sir.
Ma'am, it's not
Yes,
a
ma'am.
query. It's not
Yes,
a
ma'am.
query. It's an excellent session, ma'am. I was very new to Vivado, but it was very. You have explained so clearly.
Thank you so much,
Senthil.
ma'am.
Thank you, Senthil sir, for finding out such an excellent resource person.
Yes, ma'am. Actually, I'm also impressed with the presentation, ma'am. Okay, actually, nice presentations. Everything is go in a slow mode. Okay, actually, we are very happy to have such a person, ma'am.
No, it's my pleasure, sir.
Yeah, so
Actually, the tool takes some time to run, so that's why we are not able to show what all is there in this. Actually, there is one more world of design which we can do using only ARM processors, sir.
Okay.
So that is a different kind of design. We will not go with coding at all. We will go with working with processors and bigger designs. So maybe when we all meet up sometime, we can have a discussion on that, sir.
Yes, ma'am. In future, we will utilize your intelligence in offline mode, ma'am. Okay.
Definitely, sir.
Yes, ma'am. Yes, ma'am. Okay. Students, is there any queries? Staff? Usha, ma'am?
Sir?
We'll wind up the session, ma'am.
Yes, sir, we can wind up, ma'am. Excellent presentation, ma'am. Thank you, ma'am.
Thank you so much, ma'am.
As usual, ma'am. It was very Thank you, ma'am.
Good that students are staying even in this holiday mode, ma'am. Many of them are traveling.
Yes, ma'am. Yes, ma'am. Actually,
Yes.
that is the.
In my university also, almost half of the university is packed up, so they have gone and left.
Yes, ma'am. Actually, after long, there is a 4 days.
That's what long break for them also after many days.
Okay, ma'am. So we'll go for the final thing.
Yes, sir.
Yes, sir. Yes, ma'am. Ma'am, thank you for your nice presentation. Once again.
Thank you so much for the opportunity, sir.
Yes, ma'am. Yes, ma'am. Okay. Actually, I will go for the final thing. So, good evening, everyone. Okay. So, actually, now we have reached the end of the virtual gathering, right? So, it gives me immense pleasure to propose a vote of thanks for today's session on Xilinx Vivado. So, on behalf of ECE Department and Institution Innovation Council, I extend my heartiest thanks to our chief guest, Dr. Ms.K. Shilpa, Assistant Professor, Department of ECE, B.S. Abdur Rahman, Crescent Institute of Science and Technology, who take out time from our busy schedule to grace this event. Thank you, ma'am.
Thank you so much, sir, for the opportunity, sir.
Thank you for your trending and demonstrations about Xilinx Vivado design suit, ma'am. Actually, it really is a nice demonstration and nice flow about the VLSI platform.
Okay, sir.
Thank you once again. Thank you, ma'am. And a special thanks to our management, the principal, vice principal, for providing continuous support and guidance. And also, I extend my gratitude to our HOD, Dr. Komala James, for her immense support to make the event successful one. And I extend my special thanks to Ms.K. Durgadevi ma'am for coordinating the event. Also, I extend my sincere thanks to our department faculty members who have joined in this session. Thank you all, ma'am. Then finally, our heartfelt thanks to our students for their active participation. I hope everyone is fine-tuned with the Xilinx Vivado. So once again, thank you all. Thank you, ma'am.
Thank you very much, sir.
Thank you, ma'am. Thank you, Lord. So actually, it's a nice
Thank you,
session.
Usha, ma'am.
Yes,
Thank
ma'am.
you, Senthil, sir.
Yes, ma'am. Thank you, ma'am.
Okay, sir.
Thank you. Thank you, ma'am.
Thank you,
Usha,
ma'am.
ma'am.
Thank you, ma'am. Thank you, sir.
Thank you, sir. Thank you.
Thank you. Thank you, sir.
So,
Sir, can I
students-
leave, sir?
Yeah, yes, ma'am. Yes, ma'am. Please, ma'am.
Yes, ma'am.
Yes. Usha, ma'am, can you wind up the session, ma'am?
Sir, yes, sir, we can wind up, sir.
Yes,
Leave
ma'am.
Panila, sir.
Thank you, ma'am.
Thank you,
Thank you, Subhashini, ma'am. Thank
Thank you all.
Pranab sir and other staff who are participating in this session. Thank you. Thank you, students. You can leave from the meeting. Thank you all. I hope people are I hope people are in session and you learned about Xilinx Vivado. Okay, thank you all.
Thank you, Senthil sir.
Thank you, sir.
Thank you.
Mario, sir. Thank you.